The symmetry group of an equilateral triangle has 6 elements. The identity, a rotation this way, a rotation this way, a reflection about this line, a reflection about this line, and a reflection about this line. We can arrange the elements like this and make a composition table. You've already seen tables like this, but with letters in. For example, the element in this square is then the result of this composition. First, this reflection. Second, this rotation. From this table, we could find out everything there is to know about the group, since we can work out all possible combinations of elements. If we always write the identity first, then this row and this column will be identical to the lists of elements. So, as a convention, we drop the lists. Now, look at the isometries of the plane that carry these 3 points to themselves. They also give us a group. There's the identity, this rotation, this rotation, a reflection in this line, a reflection in this line, and one in this line. We can draw the table again in this case, but this group is very similar to the one we've just seen. After all, we were doing the same operations in both cases. If we rewrite the table, keeping the operations the same, the table we get is identical with the first one. Using this correspondence, we have changed one table into the other. A correspondence like this, which changes one table into the other, is called an isomorphism. Isomorphisms are what this program is all about. In the example we've just seen, you may have felt that it was quite obvious that the two groups were the same in some sense. But of course, it's not going to always be that obvious. Let's look at the symmetry group of this figure. Well, to help us, let's mark the starting position with a couple of dots, so we'll know what's going on. And we have just two symmetries. There's the identity and a rotation to here. So our table is going to look something like this. The identity and a rotation. And all we have to do is fill in the square. Well, that's just a rotation followed by another rotation. In our figure, we've already rotated once, so rotating once more gets us back to the identity. So we've got to have the identity in this box. Now here's Chris with another group with different elements.
And this is the symmetry group of this figure, and it also has 2 elements. There's the identity, of course, and then there's reflection in this line, like this. And I'm going to call that reflection Q, and I'm calling my identity element I. Now, if we take our reflection Q and follow it by Q, then we get back to the identity, and so that's all we need to do to fill in this table here. Now, if we use these correspondences here, you can see that these two tables are much the same. So although the groups have different elements, the two tables are the same. They have the identity down the main diagonal and the other element in these other two places. Now the correspondence we've used here is the two identities corresponding and the rotation over there corresponding to the reflection over here. Now it turns out that whenever we have an isomorphism between two groups, then the identities of those two groups must correspond in this way. And of course, we can only get a one-to-one correspondence like this between two groups if the groups in question have the same number of elements. And the mathematical jargon for this is to say that they have the same order. We've just seen that these two groups of order 2 are isomorphic, and in the introduction we had two groups of order 6 that were isomorphic. Now, could it be that all groups of the same order are isomorphic? But if we look at these examples of order 2, couldn't I have a different table, one like this?
Well, the trouble with this, of course, is that this isn't the table of a group. You see, Q doesn't have an inverse. There's no element which, when multiplied by Q, will give the identity. So we're forced, if we want this to be a group, to place the identity here. And we get the same table as before. So you see, essentially, there is only one table for groups of order 2. Well, maybe an argument like this could be used to show that if we have any two groups of the same order, then they must be isomorphic. Well, for a start, it's pretty clear that there's only one possible table for a group of order 1. And we've just seen that there's only one table for a group of order 2. Well, let's have a look at a group of order 3. It's a symmetry group of this figure. Well, the symmetries are just the identity, a rotation through 1/3 of a revolution, and a rotation through 2/3 of a revolution. Well, we can draw the table for this group. Here we have our rotations, and 0 is the identity because it's just a 0 rotation. And all we have to do to fill this in is, well, let's do one. Suppose we take 2/3 of a revolution and compose it with 2/3 of a revolution, we'd get what goes here. Let's try that on the figure. We've already done 2/3 of a revolution. Follow it by another 2/3, and the result is 1/3 of a revolution. So we want 1/3 in the square here. And it's easy enough to get the other elements just by doing the same sort of thing. And for another group of order 3, over to Chris.
And to get another group of order 3, we can use the integers modulo 3 under addition. Now, modulo 3 or mod 3 means that we consider the remainder of our number after division by 3. So 4 gives 1 mod 3, and 3 gives 0. And for example, 62 gives remainder 2 on division by 3, so 62 is 2 mod 3, and so on. And so let's fill in this table now. So the elements of the group will be the numbers 0, 1 and 2. So we can put these in the first row and column. We can complete the table just by adding and taking the remainder after division by 3. So 1 plus 1 is 2, and 1 plus 2 is 3, which gives remainder 0 on division by 3. And it's easy to fill in the rest, remembering that when we get to 2 plus 2, that's 4, which gives remainder 1 on division by 3.
By looking at these tables, can we see if they're isomorphic? Well, for a start, the identity, that's the 0, is in the same position in both tables. And in this table, the 1/3 are in these positions.
I've got 1 in those 3 positions here.
And here, the 2/3 are in these positions.
In the corresponding positions here, we have 2 each time.
So there is a pretty natural correspondence. The identities correspond. 1/3 corresponds to 1, 2/3 corresponds to 2. And under this correspondence, these two tables become the same. They're isomorphic. Well, in fact, it turns out that any two groups of order 3 will be isomorphic, and we'll see a proof of that in the next unit. Well, that's okay for groups of order 3. Their tables are fairly small. But what if we had a much larger group? For example, suppose we had a 50 by 50 table.
Well, we can usually find that when we're actually looking for an isomorphism, as soon as we start thinking about it, we get a pretty good idea of exactly what the correspondence has to be. Now, for instance, in this last example, you may have seen a representation of modular arithmetic like this, where the numbers are drawn round a circle. And to add, we simply count round. So 2 plus 2 is 1. But when we count like this, it's just the same as performing the rotations on the model. So addition modulo 3 is just the same as composing rotations.
So if we'd noticed that, we could have got this correspondence directly. Well, again, you see, those sort of things will only work if we've got a fairly small group. What we would like is some sort of test for isomorphism which doesn't involve having to draw these tables. And we can get that by going back and looking carefully at just what we mean when we say that two tables are the same. Suppose one of the groups has elements E, A, B, C, etc. and the other has elements E, X, Y, Z, etc. And we suspect that the correspondence E to E, A to X, B to Y and so on is an isomorphism. How can we test it? When we draw out the tables, if this correspondence is an isomorphism, then the element in this square must correspond to the element in this square. Now the element in this square is one of our elements in this group, and also the element in this square is one of our elements in the other group. We know from the table they are equal to AB and XY. So the elements in the squares will correspond if the compositions correspond. And if it happens that the composition of any two elements in one group corresponds to the composition of the corresponding elements in the other, then the correspondence will be an isomorphism. So that's our condition. If, for a certain correspondence, compositions in one group correspond to compositions in the other, then we have an isomorphism. Well, that's the crucial property about isomorphisms. Using it, for example, we can prove immediately a statement we made earlier, that if we've got an isomorphism, then the identity elements must correspond. And we're going to use that in a minute. But for now, let's look at the symmetry of this figure. It's going to be a group of order 4. We've got the identity. Rotation to here we'll call 1. Rotation all the way around to here we can call 2. And finally, rotation all the way around to here we call 3. And our group table looks something like this. Here we have our rotations with 0 again as the 0 rotation, and we can fill the table in. And if you think about the example we had last time, it's not surprising to realise that this is in fact just addition modulo 4.
And I've got another group order 4, and that's the symmetry group of this three-dimensional object. Now we've coloured it just so you can see what's going on when we perform the symmetries. And to label these symmetries, I'm going to first of all mark this point here. Now there's the identity symmetry, and that leaves the point fixed. And then there's a rotation like this. And that moves our point horizontally across to here, so we call that one H. Then if we go back to our starting position, see that there's also a symmetry of reflection in a horizontal plane through here. Now our reflective model is going to look like this. And you can see the point's moved down to there. So it's moved vertically downwards, so we'll call that one V. And finally there's the combination of these two. That's the reflection rotation. First of all we reflect, and then we rotate. And you can see that that moves our marked point to here. So it's moved diagonally this time, and we call that one D. And if we work out the composites of these symmetries, we get our group table like that.
Well, I don't know about you, but I can't take in tables like this at a glance. For example, are these two tables isomorphic? Well, for a start, I may have to alter the order of these things, alter around the rows and columns, so that the patterns are the same in both tables. Well, as it turns out, these two tables are not the same. And I can see that by looking at this main diagonal.
See, in the main diagonal here, we've got an E in every place. That's the identity. And so that means that in this group, the composite of every element with itself gives the identity.
Well, it's not true in this group. You see, 1 composed with itself gives 2, and that's not the identity. These groups won't be isomorphic. Well, why is that? Well, you may recall that we saw earlier that if we've got an isomorphism, then corresponding elements compose to give corresponding elements. In Chris's group, each element composed with itself gave the identity. So if we've got an isomorphism, the same must be true in this group because the identities correspond. And we've just seen that it's not true. So here we are. We've got two groups of order 4 which aren't isomorphic. And I'm afraid, in general, if you've got groups with the same order, they won't necessarily be isomorphic. Well, let's go on and look at groups of other orders. What about groups of order 5? Well, it turns out that, in fact, they're all isomorphic. And we'll see why in the next group theory unit. It's because 5 is a prime number, but we won't go into details here. And what about groups of order 6? Well, in the introduction, we saw two groups of order 6 that are isomorphic. And this figure gives another group of order 6. There's the identity we call 0. Rotation to here we call 1. Rotation around to here we call 2. This rotation is 3. This rotation 4. And finally, the rotation all the way around to here we call 5. So we can fill in our table for the group. We have our rotations along the top and the side, and in this case, filling in the table is just the same as doing addition modulo 6. Well, it turns out that these two tables are not isomorphic, and we can see that again by looking at this main diagonal. You see, in this case, the identity, that's the 0, occurs in just 2 places. So that means there are exactly 2 elements, the 3 and the 0, which, when composed with themselves, give the identity.
But in this group, there are 4 elements like that. Now remember, this is the symbol used for the identity here, and you can see it appears 1, 2, 3, 4 times down this main diagonal. And that means that there are 4 elements in this group which compose themselves to give the identity. There's the identity itself, and these 3 reflections. Remember that any reflection composed of itself always gives the identity. And now we can use the same sort of argument that we've just used for the groups order 4. If compositions correspond, then elements that compose themselves to give the identity must correspond to elements in our other group with that same property. There are 4 such elements in this group and only 2 in the group over there. So there can't be any correspondence between these 2 groups, which is an isomorphism.
The groups of order 6 have fairly complicated tables, but our next group has a table that's impossible to draw. It's a symmetry group of the infinite saw blade, and the symmetries are just the translations backwards and forwards. Well, let's mark the starting position with white dots as before. And when we've done that, we've got a fairly nice notation for these symmetries. The symmetry which moves just 1 tooth we'll call T1. And if we move 2 teeth in this direction, we'll call that T2, and so on. The symmetry which moves just 1 tooth in this direction, we'll call T minus 1. Then this will be the symmetry from here to here, we'd call T minus 2, and so on. And of course, the symmetry which does nothing, the identity, we'll just call T0. So you see, this group has an infinite number of elements, so it's certainly not possible to draw its table. But nevertheless, we can show that this is isomorphic to the group of integers under addition by using our special test for isomorphism. We'll test the natural correspondence Tn corresponds to n, Tm corresponds to m, and so on. Although we can't draw the table, we know that for an isomorphism, compositions in one group correspond to compositions in the other. Well, composition of integers is addition. So does Tn, composed with Tm, always correspond to n plus m? To answer this, we must find out what Tn composed with Tm is. Let's try T1 composed with T3. Remember, that's T3 followed by T1. T3, T1. We get T4. That's T3 plus 1. So if we try T4 followed by T minus 2, we get T2. That's T4 plus minus 2. And it's not hard to believe in general that Tn, composed with Tm, is Tn plus m. That helps us, because we know that Tn plus m corresponds to n plus m. That's just the correspondence we're testing. But we've just seen that Tn plus m is equal to Tn composed with Tm. So combining the two, we know that Tn composed with Tm corresponds to n plus m. And that's the result we're looking for. So the symmetries of the saw blade are isomorphic to the integers under addition. So isomorphism works just as well for infinite groups as it did for these finite groups. You see, it turns out that if we have any group of order 6 or less, it's going to be isomorphic to one of these. And that's the real power of isomorphism. It enables us to place our groups into classes. Groups in the same class will be all isomorphic. And that means when we're talking about the properties of one particular group, it'll be true for all the other groups to which it's isomorphic. And that underlies what we mean by abstract group theory. And it's this sort of abstraction where instead of considering just individual groups, we look at whole classes of groups, the isomorphism classes of groups, which is one of the main tools in modern mathematics.